Dr. Sobczyk, thank you very much for sending your draft. I had only a brief time to look through it, but I look forward to what you have to tell us today on so this extension of the ideas of duality, I guess specifically to the Lie algebras that are generated by this procedure. So
yeah, I've been thinking a lot about it. And now I'm thinking that I should only use the word dual for that special case where we're using nilpotents. But what I'm going to tell you today is about generalizing it and just having it equal to the inner product. And I call it compatible. So the rules are the same, except I use the word compatible, compatible geometric algebras, really. But you'll see when I.
Yeah, I think that it's good to be able to relate it to the scalar product. Like, since, as you pointed out, as I just skimmed through your document, you pointed out that that's actually the origin of duality in linear algebra, of course. So
yeah, there's a close relationship, no doubt about it. So.
Yeah, so I think that's a valuable observation. And okay, so if you're ready, I guess we can presume maybe that
okay,
Dr. Santilli, I'm not sure, I haven't heard any communications from Dr. Santilli for a few weeks, so, but if he checks in later, we can always give him a short review.
Okay, I'll try sharing screen, see if I can get my notes to appear. Let's see. Yeah, I never really have a whiteboard, but oh, desktop, that's what I want. Can I click on that?
Yes, the whiteboard would be if you were just wanting to draw on a blank screen. You can draw on the blank screen with your mouse or whatever to illustrate a point sometimes. But
now, can you see that now?
Not yet.
No, now is coming. No, it's coming.
Something is. Currently, I see a black screen.
A blank screen. Okay, let's see if I can back here. Yeah, I can see a computer, but you don't see it. So
I think it is working. Now
that's better.
Yes.
Yes.
okay, so you can see my screen now, right?
Yes, yes.
It says Lie algebras of compatible vectors in geometric algebra.
Yes.
Yes.
Okay, so yeah, if necessary, if I start breaking up too much, tell me and I'll switch to my Mexican cell phone hotspot. It seems to be better than the AT&T hotspot that I use right now. Am I breaking up?
So far, it's okay.
Okay, so some of this stuff I think I've already talked about, so I won't necessarily repeat everything. I'll just go to now. We can review these definitions. So this is this is where I define null vectors. We talked about this before. So a null vector is just a quantity such that v squared is equal to 0. That's a null vector then. And of course, any commutativity, I'm assuming you can multiply these null vectors according to the usual rules of matrix algebra. So in particular, that means that if I have A1 times A2 or two null vectors, and I add that A2 times A1, I get 0. So that, of course, just means that the null vectors are any commutatives. just
Can
algebra.
can I ask you a sort of elementary question at this point, I guess? When you write like v is a vector and you write v squared, aren't you automatically assuming a scalar product? I mean, or do you mean by that zero something else than?
No, I
than
just
say,
mean that symbol V, which I'm associating with a quantity that has the algebraic property V squared is equal to 0. So I'm not assuming anything else.
so
But
so if
I'm
no, but
assuming
if
the
you
algebra rules of matrix algebra.
but in linear algebra, for example, of vectors, if I write v squared, I mean v dot v, right? And the result of v dot v is a scalar quantity. Right?
Well,
Whereas,
yeah, that's the
later
way
on in your
vectors
item
is.
2, you said that they were anti-commutative, but of course the scalar product, at least not normally, is normally not anti-commutative.
Okay, so that's correct. Look here, I say the same rules as addition and multiplication of real and complex square matrices. Right here, I say that. So I'm not.
And so, well, my point is just that you call these vectors, and when I understand the word vector,
Okay.
I mean when I multiply one vector by another, I normally expect a scalar quantity.
Okay, that's to be defined in terms of this new multiplication of null vectors. I haven't said anything about the inner product of these null vectors yet. So I'm just assuming that they're algebraic quantities which have this v squared equal to 0 because it's a null vector.
So,
Well,
but see, but using the word vector immediately puts me on a strange path, right? If you just called these elements of some algebra, then if I say the element of the algebra times an element of the algebra is 0, I don't worry too much about that. And
well, that's
whether they're
right.
anti. But as soon as you use the word vector, then I'm wondering, what do you mean by product, right?
Okay, I could say that V is a matrix, for example, or well, that's why I say it behaves the same rules of addition, multiplication of square matrices. So that's the tip-off, that I'm not thinking about a vector. I haven't defined an inner product. I'm using the same multiplication rules of matrices, and saying a matrix squared is equal to 0 is not the same thing as an inner product.
Yeah. So if you think about a matrix representation, I understand that you can have matrices that represent vectors, but their products will be vectors. Will be matrices. Those matrices may not necessarily represent vectors. Right?
Yes.
So when you write the 0 there, it might be better to distinguish that 0 from, say, scalar 0. So v squared is a element of your algebra that it's a 0 element of the algebra, but it's not 0 scalar value.
Okay, well, the idea behind that is it's just like, well, I've written papers about so-called hyperbolic number plane, where, with I, you have I squared equals to -1, okay? But now you consider quantities, well, like a vector V, where V squared is equal to +1, for example, that's just a unit vector. Well, but again, even when you say a vector squared is equal to 1, that's right. That's when the Clifford product is identified with the symmetric part of the matrix product. If you want to look at it as a matrix, so it can be the identity.
So normally when we multiply vectors, at least in linear algebra, we think about just the scalar part, of course.
Yes, but that needs to be changed. I think that that's what I believe. very strong that it should be changed because we want a number system that not only has quantities that have square -1, which are the imaginary number I, but has square +1. And then we can.
But that's still okay. I mean, that's still a scalar, right? But it's when the product is no longer a scalar that is confusing to me. I mean,
Okay, well, yeah, I'm not. Yeah, I can understand your confusion, but like I say, I try to get around that by saying the same rules as addition and multiplication of real or complex square matrices. Now, if you want to interpret that as meaning that V is a matrix, it's okay, because I'm going to actually define the coordinate matrix of the vector V. And that's going to be that matrix, well, that's a nilpotent. Let's see here. Well, here's a multiplication table for these null vectors. So I have two null vectors, A and B. As you can see, A and B are null vectors. We say they're algebraically dual or compatible if AB plus BA is equal to 1.
Yeah.
And now using those rules, I get this multiplication table.
Mm-hmm. Yeah, all of that was clear, and you did cover that in detail. If you go back to the previous page, though, there is a statement there that maybe just needs to be highlighted a little bit more. The first point, first definition. It's here that, let me just underline this part, right? So that, in other words, you've said right there in that third sentence, right? Well, did you see what I was?
No, I can't see that. You can't write on my screen.
Normally I can.
Oh.
It should work.
No work.
Okay,
No.
maybe I should highlight this or have it in.
Well, okay, let me just read it out then. It says the trivial null vector is denoted by 0.
Yes.
So in other words, the 0 that you've written in the first line is not the scalar value.
Well, no, I'm identifying it with the real number 0. Why not?
Well, because you've just said that it's a null vector.
That's right. V is not equal to 0, but its squared is equal to 0.
But that 0 is because the trivial null vector is denoted by 0.
Yes.
So in other words, 0 is a vector.
No. V is an algebraic quantity not equal to 0, which has.
No. Read the third sentence.
Okay, the addition and multiplication.
No, third sentence.
Okay. The trivial null vector is denoted by 0. Okay, but that's not trivial. When V is not equal to 0, that's not the trivial one.
No, but 0 is the trivial null vector.
Yeah, and it has square 0 because like real numbers.
No, but I'm sorry, maybe I'm not clear. Like by scalars, I mean like a real value, a real number, like 1, 2, 3, 4, or pi or something, right? But as soon as you say vector, a vector is something outside of the set of real numbers. Right? So it's of a different type. That's the whole idea of like module, right? In algebra, abstractly, right? That's why a vector space is a module over a set of scalars.
Maybe a comment. I think that the problem is that maybe we need a first definition about algebraic vectors. I think it can be better. And then after we take only the algebraic vectors that are null vectors. but then I think can help to us to understand what is the product between algebraic vectors and the other fundamental operations.
Yeah. Yeah, well, you see, I think about matrices as being coordinates of these new algebraic quantities, which I'm starting out with null vectors. In fact, I'm going to identify that null vector with the matrix 0, 1, 0, 0, for example. You know, 2 by 2 matrices with a 0 in one, you know, in the, you know, the usual. So think about a null vector. In this, you can identify the elements of a matrix as being, each element of the matrix being, they call that a vector space. It's an n squared dimensional vector space, where the single elements of the matrix, the n squared elements of the n by n matrix, are considered the elements of a vector space. You can do that. There's nothing wrong with that. A vector space can be anything. It can be a vector space. In fact, when you take Lie algebras, really, you're considering matrices, the Lie commutator product on matrices. So elements of the matrix separate are all considered an n squared dimensional vector space. Now, it's true, I think I should make more distinction when I'm talking about a matrix algebra over the module of a Clifford algebra. So there we have a module. When I consider, for example, a matrices with quaternion entries. Now, what is a quaternion? Well, a quaternion, you're introducing 3 numbers which have square -1, and -1 is the real number -1. Well, so you can also introduce unit vectors which have square +1 and consider that to be an extension of the real number system. So what I'm trying to do is extend the real number system to include algebraic quantities which have square 0. Okay, we accept I squared equal to -1. We accept U squared equal to +1. And now we're saying, why not accept algebraic terms V such that V squared is equal to 0? Okay, well, that's just an extension of the real number system to include new algebraic quantities, which I am calling vectors, but maybe I should just say algebraic quantity, leave off null vector, just I'll call them nilpotents. I should say, instead of null vectors or algebraic quantities, say nilpotents are algebraic quantities V with the property that V squared is equal to 0. Is that better?
Maybe, as long as you're also admitting that 0 is an algebraic quantity.
Yeah, of course. Real numbers are algebraic quantities as well. So are quaternions. Why do accept quaternions as being algebraic quantities and not, well, for example, new algebraic quantities such that V squared is equal to 1? Well, don't think about it as an inner product. I haven't defined an inner product yet, but V squared, just a new algebraic quantity which has a property V squared is equal to 1. That's a hyperbolic unit quantity.
And so 0 is the unit, the additive unit in the algebra.
Yes.
But it has nothing to do with scalars.
Oh yeah, so I identify it with 0 from real numbers, just as what is a
But
0?
how can you do that, right?
Well, how can you do it with quaternions? You say the 0 quaternion is 0 real number, right? You identify.
But then I don't call elements of the quaternion algebra vectors. I don't call them vectors. Right?
What do you call it? Well,
quaternions aren't vectors, right?
Well, how about the complex number problem? You identify complex numbers with vectors in the 2 by 2 dimensional space.
No, I might say that a two-dimensional space can be a representation of a complex number. Like, but I don't say that a vector in a two-dimensional space is a complex number. Only a
Well-
representation of it.
Well, I think, well, you know, people had trouble with negative numbers. They didn't want to accept negative numbers as being real numbers. They call those fictitious numbers. It's just a language convention that we're talking about, I think.
Well, I'm not sure. I mean, it seems very deeply ingrained in the abstract definition of algebra that we begin with a ring, and then over that ring we set up a module, right? And the elements of the module form under the right. Well, I think one more assumption: the elements of the module form a vector space. Right? So the vector space is built on top of a ring. Right? So start with a ring, then you add, then from the ring you create a module. But
Okay, what is an element? What is an element of a ring called?
An element of a ring. That's all. Also called scalars, perhaps.
Well, like I say, it's really the matter of language, how we want to use language.
But the language of abstract algebra, right, it uses the terminology R algebra. So you write R is a ring, and you write, I create an algebra by starting with R, and then I make an algebra out of it. So,
okay,
so
wait a minute. Let's look at a Clifford algebra. We know it's a graded algebra. And now we say that vectors, you have a graded algebra consisting of vectors, bivectors, trivectors, and so on. Now, the interesting thing is, in Clifford algebra, you can interpret it in one Clifford algebra, what's called a bivector can be identified with a vector. And really in a Clifford algebra, what's important is the idea of commutivity and anti-commutivity, the two algebraic properties that really define a Clifford algebra, are the properties of symmetry. You know, you take a Clifford product, it consists of a symmetric part, which you identify, well, a vector part. When you identify what in the algebra are considered vectors, then you identify the symmetric product as being the usual real numbers, and the bivector part are being bivectors, okay, interpreted as directed areas. So in a sense, Clifford algebra is the geometrization of higher dimensional quantities, which are identified with vectors, bivectors, trivectors, and so on. Now, when we make the association, we say we can use the representation of the Clifford algebra as an algebra of matrices. But my point of view, Clifford algebra is just as basic as a notion of a matrix. In fact, you can think about matrices as being coordinates of corresponding elements in the Clifford algebra.
But it, you know, I think I get that. So this symmetric part, is it true that the symmetric part always has a representation as a scalar in some sense? Right?
Well, what you do is you identify elements in the Clifford algebra which are considered to be vectors. And then the proper identification that you made is that the symmetric part will always be a scalar. And the anti-symmetric part will be identified as the higher dimensional second two graded elements called bivectors. And that's how we get, for example, interpretation of quaternions in Clifford algebra. So a quaternion then becomes a Clifford number or geometric number.
But here you are defining before the Clifford product, and then the Clifford product is the product that is that permits to go from one degree vector to the next degree vector, multi-vectors. Then we can get more multi-vectors by the Clifford product. Then in this way, I try to interpret your product here like a Clifford product. But then there is the problem that Professor Pech is signaling, because the zero in the Clifford products not is the zero in scalars, for example.
Well, but the thing is that people do identify zero, for example, with the zero matrix, right? Because who wants to write a 4-dimensional 2x2 matrices of zeros all the time? So we say zero is the same thing as a 2x2, if you're talking about 2x2 matrix. By the way, though, look at these quaternions or Grossman algebra. So we know what a Grossman algebra is. A Grossman algebra consists of vectors. Well, the Grossman product is identically zero, v squared equal to 0. We can think about v as being a vector in a Grossman algebra. Maybe that's a better way of looking at it. In fact, that's the idea, that we're going to get Clifford algebra by taking two compatible Grossman algebras, or by defining what I mean by duality between those two Grossman algebras. So think about it like that. Definition number one, null vectors are one vectors in a Grossman algebra. Well, they're the basic. Okay, in a Grossman algebra is graded into one vectors, bivectors, trivectors, and so on, just like a Clifford algebra is. You agree with this, don't you, Bill?
Yes. Well, but I would also say that zero is not an element of the Grassmann algebra.
Well, what is
I
zero?
would say
then?
zero is a scalar, right? And we do have a product that is defined between scalars and elements of the Grassmann algebra.
But we do write the addition of Grossman one vectors. So you do have the idea of a multivector in a quaternion algebra, right? Because
yes. So a zero vector is not equal to zero scalar, because they have grades, right? One is of degree 1 and the other of degree 0.
Well, okay, that's true. So you have zero bivectors, you have zero vectors, you have zero trivectors, correct. You have zero, but yes, that becomes very clumsy. It just makes sense to identify zero with the, maybe if you want to define it in terms of tensor products, take all those zeros and tensor the algebra out with all the zeros and go.
Okay, but then, so if I just write 0, what's its grade?
You can say it as any grade you want to. You can say it's a 0, 1 vector, 0 bivector, 0 anything, but it doesn't really matter, because when you add it to anything, 0 plus anything is the identity element in the whole algebra. So you can say it's a class of all the 0 vectors, 0 bivectors, 0 everything. Put it all as zeros.
So
it
0
doesn't hurt anything to do so.
Well, I know it's a bit pedantic, of course, because I mean, when I write 0, then I don't mean an element. I mean, when I write 0, I'm being ambiguous. I mean, pick a compatible grade, and then you know what it is, right? Then you know it's either the 0 vector or the 0 bivector, because you know that.
No, what I would rather do is take all the vectors and intersect it with the set of all bivectors. And I would say they have one element in common, and that's 0.
I think that if we can think this in this way, if we take the Clifford product of 2 vectors, then we go up to multivectors.
So that's the Grossman quadrant.
We go to B vectors with the Clifford product. But if I
The anti-symmetric part of the Clifford product.
excuse me?
The anti-symmetric part of the Clifford product.
I like to end my argument. But if you take the inner product, you go down to scalars, to reals in this case. Then this is different because for one way I can build multivectors of higher degree. Then in this way we have to make a differentiation between the zero scalar and 0 vector and 0 multivectors, because then we are in different categorical objects, in different,
different gradings of the algebra.
Yes, we are grading the algebra, and then I think this is too much important in the definition of duality, because
Yes.
if we go to scalars, then we are taking elements of different space that are going down in the degree. And if we take products, algebraic product, then we are building multivectors of higher degree. But here the product is not the dual, is not in, is not taken by dual elements, but are elements of the same set, Then I think that this is the idea that this is important to distinguish between the 0 in each degree of the algebra.
Okay, so let's look at number 2 here. It says 2 null, well, I say null vectors, but let's say 2 elements of a Grossman algebra are said to be anti-commutative under the Grossman product, right? So A1 plus A1 times A2 plus A2 times A1 is equal to 0 as a 2 vector in the Grossman algebra. Okay, so that's okay, right? That's just a normal Grossman product that I'm talking about in definition 2. We have 2 quaternions in quaternion algebra, and we say that they're if you have 2 elements in a quaternion algebra of vectors, the vectors of a quaternion do satisfy they're anti-commutative by definition, right? So it's better to think about A1, A2 up to AN being, if they're all anti-commutative, that just defines a Grossman algebra. Okay, now, but who wants to say that the 0 is a bivector or trivector, the trivial trivector, trivial? I just want to identify all, define a 0 to be any element of an algebra, which has the property that when you add it to any other element of the algebra, you get that element back again. So it could be a Grossman algebra. 0 is just the unique additive identity in that algebra, if there is such an element. Now you can say it's the trivial graded element of degree 2, but you don't want to do that all the time. It just becomes too clumsy to make that identification all the time.
What about for the scalar value 1? What happens with that?
No, 1 is just 1.
1 is
real
1 what, though?
Well, 1
Like,
is a real number 1. On the real number line, 1, 2, 3. It's
But
only
are there
0.
no-
1 is not the identity element. When you add it to another, there's only one element, the 0 element, which when you add it to any real number, you get that real number back
Yeah.
again. Or in the Grossman algebra, there's one
Yeah.
element.
No, but 1, if I take an element of a Clifford algebra and I multiply it by 1, so
You get the element back again.
so it's 1 is the identity of the Clifford algebra.
Uh-huh. But I
right?
also consider that to be a real number as well.
But do we have, for example, a degree 2
Well, for example, in a
value
ring,
for 1? So
wait a minute.
in other words, are there
If you have a ring-
any? No,
if
but
you
are
have a
there any?
ring,
Are
when
there
you
any
say a
other?
unit in a ring, you mean, okay. Think about it as a ring if you like. So when you say a ring has the identity 1, it can be the real number 1, or it could be, for example, modulo p. Okay, it can be a prime number, modulo p 1. Okay, it's not the real number 1, it's the real numbers modulo p. Okay, so but you use the same symbol 1 for modulo 3 numbers. You have 0, 1, 2, and then it's a multiple of 3, so you have 0 then. So we are flexible in the way we use the concept of 0. So why not just define 0 to be any algebraic quantity, which when added to another element of the same algebra, you get that quantity back again. So that's a more general definition. Okay, but then okay, if it's a graded algebra, then so we just, I think we need to generalize, or we just get, it becomes too heavy. The notation becomes a problem.
Well, I'm just wondering, so you started off by saying that you are interested in elements whose square is 1 and elements whose square is -1. And now you're extending that to say elements whose square is 0.
Exactly.
So when I say that an element squared is 1, if we're talking about an arbitrary Clifford element, then a Clifford element times a Clifford element is going to have a kind of grade, right?
Yeah. If you
So
take two orthogonal unit vectors and multiply them together, you get a bivector. Now that bivector can have square +1, or it can also have square -1. We say it's a Euclidean bivector if it has square -1, and that's identified with I in the complex number system. Now, if it has square +1, it can be a bivector where one vector is has square, square +1, the other has square -1, and then they're anti-commutative. So the important idea is the notion of anti-commutativity. And that's what I'm trying to emphasize in the definition of a matrix. There's two things that are important when you talk about geometrically, when you talk about matrices, and that's the idea of any commutative matrices or commutative matrices. So the property of any commutativity and commutativity of a matrix are very important ideas. And that's why I'm trying to get at the idea of a matrix in terms of null vectors. You can write any matrix as a product of null vectors.
But you just said, I think you said something that's quite critical, and that is that you associate the anti-commutativity with the element, right? But when I think about anti-commutativity, I associate that as a property of the multiplication of the operation.
That's okay. For example, number 2. Okay, we have A1 times A2 plus A2 times A1 equal to 0. That's quaternion, or that's Grossman algebra multiplication. That's the way I want you to think about that. Is there anything wrong with that? Number 2. Let A1 and A2 be elements of a Grossman algebra, of vectors in a Grossman. We know what a vector and a Grossman algebra is, don't we? That a Grossman is a graded algebra.
So that doesn't cause me.
A2 are vectors in a Grossman algebra.
But that doesn't really cause me too much trouble, other than to wonder, what is on the right-hand side.
Okay, call it the 0 quaternion or 0 bivector quaternion if you want to. But like I say, defined in the algebra, a 0 means the unique element in the algebra such that when you add it to any other element of the algebra, you get that element back again. So.
Okay,
It's just an identification that you're making of all the 0 vectors, 0 real numbers, 0 vectors, 0 bivectors. We call that 0.
But in Grassmann algebra, I know that the grade of the 0 that I wrote on the right-hand side is a bivector, or
okay, well, it's okay.
That it has degree 2, right? I know unambiguously that the 0 has to be degree 2.
Yeah, well, but we can also.
But in Clifford algebras, I don't, right? In Clifford algebra, the arbitrary Clifford product, I don't know necessarily what the grade is of the 0. Right?
Well, that's right. In fact, and you can have 2 Clifford algebras which are isomorphic, where you're identifying one Clifford number with a vector in one Clifford algebra is a bivector in another Clifford algebra. That's okay. So the idea of grading is in a different, you can have isomorphic Clifford algebras where the grading of the algebra is different. What you call vectors is different than bivectors in the other one. But so the idea of a grading is very important in Clifford algebra.
Yeah, and I think that was interesting in your early observations when you were talking about iso-Clifford algebras, right? Because you're doing almost essentially that, right? That you are kind of mixing grades in an unusual way, right?
Well, yeah, that was the idea. I was interested in Dr. Santilli's ideas because this idea, I've never seen that ISO definition of multiplication. And now I'm wondering whether it is closely related to this talk I was giving, I wanted to give today. So
yes, yeah. So I'm sorry for interrupting, but on elementary points, right? But
I think it's important, but I think that I hope that we have a general definition of 0 now in an algebra as being in this case the unique element of the algebra, which when added to any other element of the algebra gives you the same element back. Now, normally you identify, for example, in number 2, you identify that 0 as being the bivector, but you can think about that as a factor algebra of all the zeros taken out, identifying it with one set in the algebra, just the 0 element in the set then. And I think that's important to do that. But you can see it's really a matter of what you mean by grading too, because like I say, Clifford algebras can be algebraically isomorphic, but what you identify as a vector in one Clifford algebra can be a bivector in the other one. So
Yeah.
grading is a different concept than
Yeah, and this actually, just by, as an aside, this was a point that Oshevich made kind of repeatedly. He really disliked the definition of Clifford algebra that started with grading, right? He didn't want to say that an element of a Clifford algebra was necessarily graded, right? Instead, he preferred the definition of Clifford algebra that comes from Chevalier, right? The French mathematician. And the definition there, Chevalier's definition of Clifford algebra didn't use the concept of grading at all. In abstract.
Yeah, I guess the tensor operation of the ideal quadratic form, grading the algebra with, that's where the grading of a tensor algebra comes in when you take the ideal generated by the quadratic form, the symmetric product of tensors, of one tensors, I guess. Okay, so what I'm doing in step 4 here, okay, so maybe I take AI, okay, so what do we mean by this then? AI is 1 AI. So 1 again, okay, that's the scalar 1, just think about it as a real number, and AI is the element in the Grossman algebra. We have 2 Grossman algebras, one generated by the A's and the second Grossman algebra generated by the B's. So I define the basis elements of the Grossman algebra G2 over the field. What is this? Okay, I guess, yeah, F is just a field here. So I should be an F anyway, the notation's bad there. So notice I'm defining what I mean by the right Kronecker product. So I take A, well now look, I'm mixing matrix notation. I'm considering that to be a column vector consisting of 1 and AI. Okay, so by this product I mean, I take it inside and then I get this 4 vector then. Well, a combination of okay, that's, so what do I mean by 1? So 1 is the unique element in the Grossman algebra, which when multiplied by any other element in the Grossman algebra gives you that element back again. Again, I guess that's, that's the identity element. So if you multiply 1 times a vector in the Grossman algebra, you get that element back again. 1 times a bivector gives you, so that's the Grossman algebra over the real numbers, then I would say that. Okay, so anyway, you get, that's the basis of the Grossman algebra G2, 1, A1, A2, and then you have the bivector A1 times A2, which is the product of A1 times A2 as a Grossman product, as in the definition 2. Okay. Okay, so the basis of the Grossman algebra Gn over the real numbers. So that should be an R, just the real numbers here. Or it could be complex numbers.
A remark I need in the prior question in the Kronecker product, then we can say that the first element 1 is scalar 1. A1,
Yeah, exactly.
A2 are vectors, and A1, 2 are B vector.
Exactly.
Okay, thanks.
Yeah, like I say, I consider, I'm going to put them all in a generalized real number system. So a generalized real number system in my mind consists of just the ordinary real numbers, and then you have vectors, or just general, well, vectors are squared, Euclidean vectors have squared +1, pseudo vectors have square -1. Oh, anyway. Here we, okay, so the Grossman algebra has basis for here, and then the generalization is this expression here. Okay, we've been through that before, of course. And then we define left-directed product the same way. I've added this step in here to help keep it straight, so you can see the left the left product gives you 1, A1, A2, but reverses the order of the product of the basis elements then. Okay, then I introduced this table. So that's the most simple case. A pair of null vectors are said to be dual. So I would leave off the word, it's okay. Well, I say it's compatible, but maybe dual is a better way of looking. See, that this duality here is going to characterize the matrix product. So when I say algebraically dual, I mean that AB plus BA is equal to 1. And that's going to define what the matrix representation of the Clifford algebra is, basically. Okay, and then that's why I introduced that notation there. Okay, now you see I'm identifying the Grossman G1. And now you see what I do here. I'm just using ordinary matrix multiplication. BA now is the product of these compatible null vectors which satisfy this property here. So again, I'm thinking about this new algebra generated by these null vectors in A and B. That's what my generators of the Clifford algebra, G11, are. So, and this is the way I get I take A, I put BA in the middle. Now, if you look at the properties of that, that's an idempotent. Okay, so BA times BA is equal to 1. Well, that comes here. BA times BA is equal to BA. It's an idempotent. Okay. And we get, so this is now the matrix representation of the Clifford algebra G11. Okay. If I'm breaking up, I can switch to my other hotspot.
Yeah, you are a little bit breaking up.
Let me go ahead. I'll switch over to the other hotspot. It's annoying that
it was okay, but then suddenly it started to break up a bit. I guess it depends on how much bandwidth that you have available on your network. You may lose your Zoom session. Yeah, which I guess he did.
Can you hear me?
Yes.
Yes, yes.
Okay, so I switched my hotspot to my Mexican cell phone.
Works better. Can you go back to where you wrote the compatibility? Yeah, there. Number 1, the equation number 1.
Okay, let's see, where is that? Oh, okay, here.
Yeah, see, I mean, I have again a sort of just a related interesting observation, right? Is that you've written AB plus BA equals a scalar value, right?
Exactly, the real number 1.
Which if these are Grassmann algebras, that's odd, right?
Well, here I'm actually defining a product between these Grossman algebras, or what I call compatible Grossman algebras. I think we say the algebras are compatible because they satisfy equation number 1. Okay, that's what I mean by a dual, that the algebra is generated by the A's, which are anti-commutative and generate the first Grossman algebra, are compatible with the second Grossman algebras generated by the B's. And we're now introducing a multiplication between those two Grossman algebras by defining this relationship, AB plus BA is equal to 1.
Yeah, so now we're in a new algebra, right? We're
That's
no
right.
longer in either of those algebras that you
In
started.
fact, we're in the Clifford algebra G11.
But you've the critical thing maybe is that you've insisted that sum is a scalar, right? So we know that the grade of 1 is 0, right?
Yes. Well, we're just identifying 1 with that unique element in the algebra, which when multiplied by any other element in the algebra gives you that number back again. So that's the same problem as with 0.
But if we do have such a thing as an identity matrix, for example,
Yeah.
the identity matrix is not equal to the scalar 1.
Well, that's true. That's why I'm saying in Clifford algebra is more basic idea than a damn matrix algebra. Matrix algebra is just coordinate matrices of Clifford numbers. There are many different representations in terms of matrices, but you consider a matrix just to be the coordinate matrix of whatever you're talking about, that it's isomorphic to. So I'm characterizing matrices in terms of what I call compatible or dual Grossman algebras. So the Grossman algebras have that anti-commutativity property. The A's are anti-commutativity and B's are anti-commutativity. And now so it's a way of characterizing a matrix algebra in a way. But the idea about a Clifford algebra, you can generate higher dimensional Clifford algebras by taking the Kronecker product of the lower dimension. Of course, people do that with matrices as well. They generate a tensor product of two matrices to be a higher dimensional matrix as well. That's the thing. We've all been indoctrinated by hundreds of years of mathematics. The last 200 years determine the way we think. I resent that. I don't want to be indoctrinated by 200 years of mathematics. I want to think my own way.
So what you'd like, I think, to insist is that you have no definition of grade here. That this is nothing to do with grades, right? So
well, no, I'm going to introduce grade very quickly. Well, you can see, look down here, F is equal to A minus B, and E is equal to A plus B. Now you calculate. If you calculate using these rules in this multiplication table, you find that E squared is equal to 1, and F squared, which we identify as A minus B, is equal to minus 1. Okay?
It looks like your expression 1 is for going to a lower degree.
Okay, yeah.
Then Clifford product is for going higher degree. And this expression is for going to down degree. If we can interpret it
exactly. That's right.
in this way, maybe we have not problem with going up and down in degrees.
Look at this. Look at expression number 1 and expression number 2. AB plus BA is equal to 1. Well, here you have BA plus AB is equal to the identity matrix. So you see the identity matrix 2 is exactly equation number 1. That's why I make that identification. AB plus BA is equal to 1. And here it is. BA, that's the element, that's an idempotent. Well, you take the matrix 1, 0, 0, 0. You multiply that by itself, you get 1, 0, 0, 0. So that's that's the matrix one. The identity matrix represents the element 1 in the Clifford algebra G11.
But
And look at the A. A is a nilpotent. If you take the matrix 0, 0, 1, 0, that represents the element A, because A squared as a matrix equals 0.
in your table, there is not the product by one, but okay, we can get that using your expression one.
Exactly.
Expression one, and then okay.
Let's see. Okay, well, I was going to write. So this the usual basis that's given for G11 is the vectors E and F. So now we're putting the grading on the Clifford algebra. So I'm saying that E and F are vectors, grade 1 in the Clifford algebra. So any linear combination over the real numbers is a vector then. That's our 1 vectors in the Clifford algebra. And again, I didn't calculate it. If you calculate E times F, you'll see that E times F plus F times E is equal to 0, again, by using this basic multiplication table. Okay, calculate that. It's very easy to do using the multiplication. Calculate EF and FE, and you'll see that it's exactly EF is equal to minus FE. So they're anti-commuting vectors. And that's what generates the bivector EF. There's a bivector now in the Clifford algebra.
No, but just maybe I didn't follow that. Where did you define the concept of vector?
Right here. I'm saying that E is a vector. E is a vector. I'm just saying that A and B are null vectors. Well, remember, they're the 1 vectors in the quaternions. So A is a 1 vector in the quaternion algebra generated by the A, and B is a 1 vector.
No.
Okay.
One moment. But A is an element of the Grassmann algebra, isn't it?
Yeah. Compatible
and B is an element. And B is an element of another Grassmann algebra.
Exactly, but they're compatible because they satisfy equation 1.
But how did we define that we could add A plus B?
Okay.
Well, that's just adding quaternions. That's just the addition of the 2 quaternions. Oh, wait a minute, let's see. A plus B, well, that's right, I've defined that. Okay, so yeah, that's another step that I think about them as being.
Well, but if this is a definition of vector, then you're just going to say that that sum is exactly what you mean by a vector.
Yeah, exactly. So yeah, we take the 1 vectors and the 1 vector, and we just add them together, and it's commutative. We assume that it's commutative and all the rest of it. Remember, we say it obeys the same rules as matrix addition and multiplication. Okay, and I agree that you can be very pedantic, and we never make any progress. Then that's the first step of learning anything.
Yeah, yeah, for sure. And I agree that maybe it is pedantic. Like maybe the distinction that comes naturally to my mind is not relevant to your overall development, right? And that
that comes from 200 years of the last 200 years of mathematics been taught to us.
The critical thing in the end is that what you're doing has to be self-consistent, at least.
Well, that's right. So you have to give me some confidence in me as a mathematician to accept that probably what I'm saying is, except when I make mistakes, of course, but this is pretty well thought out, actually, over 50 years, actually.
Well, but I just, pedantically, then I'm worried about the definition of vector. I guess that's what I started off with also worrying about, is as soon as you multiply two vectors together and you get 0, but you didn't say what vectors
Well,
were.
I'm saying that those are really Grossman algebras. So Grossman, that's just the Grossman product of the A's. They're in a Grossman algebra. So by multiplying two Grossman vectors together, you get a Grossman bivector. The same with the B's. You multiply the B's together, you get two bivectors in the Grossman algebra B. You get a bivector in that Grossman algebra. Now we're putting those Grossman algebra, they're compatible because they satisfy the equation number 1. And I'm assuming that when you add Grossman vectors from the two, you can do that as well. We're identifying those vectors in the Clifford algebra then.
But I could take, say, 2 bivector elements from a Grassmann algebra, multiply
add
them
those
together,
together,
and get
exactly.
0, right?
Oh yeah, sure, that's right.
So does that mean Grassmann bivectors can be vectors in your sense?
No, a Grossman bivector in the A, well, no, if you add a Grossman bivector algebra generated by the A's plus a Grossman bivector generated by the algebra B's, the Grossman algebra B's, then you get a bivector by definition. So we're saying a vector in the Clifford algebra consists of adding together the bivectors in the Grossman algebra generated by the A's to the bivectors in the Grossman algebra generated by the B's. That's what you identify with a bivector in the Clifford algebra then. So a vector then is just the sum of the Grossman vectors A plus B. Okay, that's the simplest case. And that generates the matrix algebra, 2x2 matrix algebras. And that's why I'm saying
So
that G11.
you don't necessarily know that the grade of A in the Grassmann algebra that it comes from, the grade of A is not necessarily 1.
Well, yeah, that's right. That's the second case here, and that's what I do. Let me just go down again. Okay, here's the second case then. Okay, let's see here. Well, okay, here I'm just generating bases for the higher dimension. Okay, here, look, equation number 3 is very important. Okay, so now let's look at GNR. So this is the geometric algebra, the Grossman algebra generated by A1 to AN. These are vectors. These are 1 vectors in the Grossman algebra, what I'm calling Gn of R. Now, Gn star, or what do you call that symbol, is equal to hash, right?
Or sharp.
Yeah, okay, sharp. Yeah, that's better. Yeah, okay. So that's generated by the B. So the vectors in the Grossman algebra Gn sharp is B1 to Bn. And then you take the product of these things and you generate the second Grossman algebra. Now we say these 2 Grossman algebras are compatible or dual if this condition is satisfied. Okay, and now I'm identifying the Clifford scalar product or inner product with AI Bj plus Bj AI is equal to delta Ij. So that's that you're assuming relationships between the elements of this Grossman algebra Gn and Gn sharp. Okay, namely we're assuming anti-commutative relationship. Well, this is very important for understanding the structure of n by n matrices. And that's why I say the structure of a matrix I think about as just being a coordinate matrices of a course of a Clifford algebra. Okay, so this is the generalization of that. If the Grossman it consists of only 1 vector, that reduces to equation number 1, AB plus BA is equal to 1. But now here note I'm also assuming the anti-commutativity relationships between all
But-
other elements in the Grossman algebra.
But where did this dot come from?
Well, that's symmetric. I'm going to identify that with the Clifford dot inner product of two elements in the Clifford algebra. But
So-
what's important is what I'm identifying with vectors. Vectors are Grossman vectors in G generated by the A1 to AN, and the vectors of the Grossman sharp generated by B1 to Bn. Okay, now I'm defining a product, compatible Grossman algebras.
But here you wrote dot, and in expression or your equation number 1, you didn't write the dot.
Well, that's right. I spared that. I didn't want to distract you with that. But
So,
that's
but if
that's
you
that's
that-
included here then.
no, but go back to your number 1, right? Yeah. So
So I
so
would
here
write
you didn't
A1
write,
B1 plus B1 A1 is equal to 1.
but you didn't write
That's
A
equal
dot
to
B.
2A. That's right. That's 2A dot B. See, now I'm introducing a dot product. But you see, that's the interesting thing because A and B are really null vectors in the compatible Grossman algebras, which satisfy this multiplication table. I'm trying to
But if I
undocument.
but if I wrote A dot B, I would think that it's necessarily true that B dot A is equal to, that's what you just said, right?
Well, yeah, A dot B is equal to 1/2 because
So-
2A, this is 2A dot B. So A dot B is equal to 1/2. 2A dot B is equal to this expression in Clifford algebra. Okay, AB plus BA is equal to 2A dot B. In fact, that's the way I want to generalize this equation 1 by instead writing that as 2A dot B, not having it equal to 1. What happens when you just have it equal to A dot 2A dot B? That's the whole idea of this new presentation, really. So I'll go back here. Okay, so you can see this is just a generalization. If you have only one vector, A1 and B1, then you have 2A1 dot B1 is equal to well, that's 0. Well, no, it's equal to 1. Okay, that's A1 B1 plus B1 A1 is equal to 1. So A1 dot B1 is equal to 1/2. Then.
But it's critical here that you introduced a new multiplication.
Well, I'm multiplying. That's right. I'm introducing a multiplication of these two Grossman algebras, G
And that,
and G and sharp, by insisting that how you multiply them. First of all, you add them just by adding it. These bivectors are added to the bivectors, trivectors added to trivectors, and so on. Well, I identify, yeah, well, anyway. Okay, so G and N, that's this Clifford algebra, is generated by A1 up to AN. These are the vectors in the algebra. A1, these are the Grossman vectors in Gn, Grossman algebra Gn. These are the vectors in the Grossman algebra sharp Gn. Okay, two Grossman algebras there, and I'm adding them. It's just ordinary addition, or considering bivectors are in one Grossman algebra are added to the other bivectors in the other one. Okay, now you can see that we have all these idempotents, which are BI, AI. Well, and now you see I'm generating the basis for the geometric algebra GNN. Okay, let me just go ahead with that.
but so.
And now you see how.
But just one clarification, because you wrote the dot before, but now you're not writing the dot anymore.
Well, that's just ordinary matrix multiplication, corresponds to ordinary multiplication. When I don't write the dots, I'm thinking about ordinary matrix multiplication.
So even though you wrote dot up in your equation 3, you still mean matrix multiplication.
Well, that's right, exactly. But dots, I'm writing between vectors. I'm assuming I know what a vector is when I take the dot product, because as Dr. Cruz said, dot product in Clifford algebra lowers the degree, okay? Or you can define it on the Grossman algebra as well. So at a lower degree in the Grossman algebra, Gn, you dot it with elements in the Grossman algebra, Gn sharp, and that lowers the degree. I'm supposed that you do that.
But your delta ij is not equal to the scalar 1. Right?
Well, it's equal to 1 or 0. Delta ij is the usual Kronecker product, which gives you 1 or 0. But that's in my general sense of what it, you can see, you have to get over your indoctrination of 200 years of mathematics, break free of this indoctrination. Of course, I argued with Dr. Ojevich many times about these things, and well, you know.
But if in your equation number 1, shouldn't you have written just delta without any subscripts?
Well, but
or no, equation number 2, I guess. Sorry, not 1.
Okay, let's go back here. Let's see, where is it?
Equation 2. Or no, no, it is 1. Sorry, go back to 1. Yeah, sorry. Here, shouldn't, instead of writing 1 there, shouldn't you write delta?
I could. That's right. That would be A1. That'd be delta 1. But you know.
Okay.
Yeah. So again, I'm identifying 1 is any element in the algebra, the unique element in the algebra, which when multiplied by anything gives you that element back again. It's the identity element. It's unique. That's what I call the scalar 1. The real number 1 is the same. I think about it as being the same. Okay, well, I'm just trying to, with second degree matrix algebra, 2x2, 4x4 matrix algebra. So geometric algebra G22 has this basis. So notice that U1 and U2 are now idempotents. And I define those by, okay, so you have to, where are my idempotents to find? Try to be careful
8.
here.
Yeah, item line 8.
Oh, do you see it? Oh, okay.
Yeah.
Okay, yeah, right here. UI is BI times AI. So just like with U1 is just B1 times A1. Now that's the same thing as I wrote as B times A. That's an idempotent. Now, if you look at U1 times U2 in this case, you'll find that they commute with each other. So you can see what I'm doing. Okay, let's see. Wait a minute, let's see, where is it now? Okay, this is the corresponding basis for the Clifford algebra G22. So again, I will define my vectors A1 or E1 to be A1 plus B1, E2 equal to A2 plus B2, and F, you know, is equal to, did I do that? I don't remember. I guess I did that too. I hope, I think I did it. Okay, here. So EI is the standard basis of GPQ. Well, in this case, I'm thinking about NN, GN. EI is equal to AI plus BI. FJ is equal to AJ minus BJ. Now, if you calculate the square of those things, you find it's equal to 1, and the FJ squared is equal to minus 1, and they're anti-commutative. Okay, that's what I say here, anti-commutative vectors, and they satisfy this property. EI is equal to 1, FJ is equal to minus 1. So now you think, now I'm thinking about the real numbers as being extended by, to get the Clifford algebra, GNN is being extended by a set of n commutative, n anti-commutative vectors EI and FJ. They're all anti-commutative. And they generate the Clifford algebra GNN, okay? And now in this property, if I add one more anti-commutative vector, which has square minus 1, then I get, that's isomorphic to the geometric algebra over the Clifford, over the complex numbers. So in this case, we can give the elements of Gn over the complex, the Clifford algebra over the complex number generated by n vectors, which have square plus 1, to be the Clifford algebra n plus 1. And now you can see, if you look at this, we can identify I in this, the pseudoscalar element consisting of the multiplication of all the basis elements, E1 up to En times F1 up to Fn plus 1. That can be, that's in the center of the algebra, and that has square minus 1. Well, it's easy enough to see that if you think about it. But again, it's just details that you have to go through to. Well, I try to give references here that you're, okay, but okay, this is really the last section I added there. So instead of equation 1, remember equation 1 was A plus BA is equal to 1. Now I want to generalize that equal to just the ordinary Clifford product between A and B. So AB plus BA is equal to 2A dot B. And I want to do everything else the same, but using this definition. Okay. So now if I define this multiplication again, 1A, BA, what do I get? Well, I get this expression. Well, it's slightly more general. Remember, for when I had this equal to 1, I simplify this. ABA was just equal to A, and BAB is just equal to B. And this was an idempotent because we saw that BA times BA is equal to 1. But now when I multiply the second row of this thing, I get ABA, that's this element here, and I get A, and I get AB times AB. But I cannot reduce that now because I've assumed this more general rule here, that A plus BA, instead of just equal to 1, that's what I have the compatible dual vectors. I have the general Clifford product, inner product between those two vectors. So now I'm asking the question in this third section, what are compatible vectors? I won't use the word dual anymore because I restrict that. The word dual is when that's equal to 1. Because when I equal to 1, then this thing simplifies to BA, AB, BAB is equal to B, and BA is equal to A. So this is more general because I identify that now. But notice what I call vectors. I'm not changing the definition of vectors. A vector is the sum of the two compatible Grossman algebras, one-dimensional Grossman algebras in this case. But now I have to generalize this expression here. Okay, and now I use a new mapping. So I map the geometric algebra G11 onto what I call the geometric algebra G1 prime 1 1, where A prime B prime is equal to a real matrix, 2 by 2 matrix times A and B. So really, I'm thinking about A prime as just being a scalar sum of SA times TB in general. Becomes a vector now in this. So the vectors in this geometric algebra prime are exactly the same as the vectors in the geometric algebra G11, but now it's slightly more complicated because I'm not saying that AB squared is an idempotent. So I'm trying to go through that. I hope that maybe Dr. Santilli would be okay. So now I'm getting.
Excuse me, but we can use here your table, no? And simplify the equation 6.
Yeah, that's right. And that's what I do here. When I go down a little further, you see, so all A, B, that's just an expression in Clifford algebra. So remember, AB plus BA is equal to 2A dot B. So BA is equal to 2A dot B minus BA then, simple. And notice then BA then is just the same thing, except pulling the, we have 2A dot B minus AB. So that allows us to reverse the order of the product in Clifford algebra. And that's in the, okay, and then ABA, well, that's easy enough to calculate because I just multiply AB on the right by A and I get this expression. Remember, A squared is a scalar, so I can pull that to the other side. So if I take AB and multiply it times A on the right, I get this expression, A dot B times A minus A squared B. And I multiply B on the right, and I do the same thing. I can say BAB is equal to 2A dot B times B minus AB squared. So now I'm just using.
But isn't A squared 0?
Yeah, that's right. Let's see. No, I'm not saying that anymore. I'm not saying that. You see, not. No, that's true. I'm not saying that any longer. But I'm saying what a vector in the Clifford algebra consists of vectors. Yeah, you see here, look, in this expression, G bar, yeah, it becomes more complicated. So now I'm saying A goes to A bar and B goes to B bar. But remember, a vector A bar now is a general vector, consists of S times A plus T times B. Okay, so that's what I mean by vectors now. So it becomes a little more, you have to be a little more careful here. But I'm just using, so a vector, now what is a vector? A vector is a vector in the Clifford algebra G11. So that's just the sum of the vectors, the Grossman vectors in.
Oh, okay, sorry, I should read more carefully. So A and B are elements of a Clifford algebra. They're no longer elements of Grassmann algebra.
I'm taking the module to be the Clifford algebra G11 now.
And no longer Grassmann algebra.
That's right. So I've changed my module. I started with, that's the idea. The main idea is that when you're looking at just the isomorphic matrix algebra, you take that equation AB plus BA is equal to 1. But when you're considering as a module over the Clifford algebra G11, then your vectors are A plus B and A minus B. That's the basis vectors then. So that's right, it changes that. But now you see, I'm just.
But they're no longer, so they're no longer nilpotent, right?
That's right. And that's what I'm doing here. I don't really want to carry the primes. So you see, I don't really want to use A prime and B prime all the way. I've done that here then. So F prime is using all the primes. I want to drop the primes. I don't want to use the primes because it just becomes too, so I'm thinking about A and B as being elements in the vectors in the G algebra G11 now. So I've changed the notation. But now I have the more complicated expressions here then, which involve many higher order identities in the Clifford algebra, which I've calculated here. Okay, well, now I'm using more general expressions. But what I'm really interested in doing is looking at the Lie algebras. So generally, when you look at the Lie algebra, special linear algebra SL2, okay, that's the simplest Lie algebra of 2 by 2 matrices. And notice that we use 0, 0, so 0, 1, 0, 0. Well, that's the matrix of my Clifford number B. When I in slide number 1, I used B as that corresponded to 1 in the matrix representation, and A corresponded to 1 in this position. There was a nilpotent in this position, and BA, of course, was okay. Oh, okay. So this is what I'm trying to say here. So if we instead reduce to that, where we assume that 2A dot B is equal to 1, then this thing just reduces to BA times the identity matrix. Because BA becomes the idempotent. BA squared is equal to BA. BA cubed is equal to BA. A squared and B squared are 0 in this case. And get 0, that becomes just BA times the identity element then.
If A squared is 0 and B squared is 0, then your expressions above can be simplified quite a bit.
That's right. And that becomes the ordinary matrix product then.
So
You see?
so for example, in 9,
That's what we
in
have to deal
equation-
with. Yeah, very complicated expressions in geometric algebra involving these matrix identities, which I've tried to write down, the ones you need here, but it's awful. And I think that's what stopped people from learning Clifford algebras. These identities are terrible. I struggled several days getting these. I make mistakes all the time. Finally, I calculated these identities using I checked them using Mathematica, using matrices. Okay.
no, but
The matrix
but isn't it true that every time you write A squared, you could just replace that with 0?
Well, that's when you have equation 1 and equation 3 true. Okay, that's the more general expressions here. I could
But
go back here.
You just said in 9. No.
Let's see. Okay, that's equation 1. Okay, 2, 3. Okay, that's the generalization for the n-dimensional case. Okay, and that the corresponding bases. So these are the bases where we have this generalization here. You see, but now when I replace that, that's 1 and 0. That's the only one that gives you the ordinary matrix multiplication then. That simplifies things tremendously. Now I'm looking at the effect on the simplest Lie algebra SL2. Okay, that's the matrices, the diagonal, the trace is equal to 0, SL2, if you remember. Okay,
When
so
you
that's
say
the more general.
But
I'm
when you
thinking,
say that A is an element of a Grassmann algebra, when you write A squared, you mean 0.
yeah, but I've changed that now. A is now is a vector in the Clifford algebra G11. Well,
So
here I use this.
But you no longer, if it's just an arbitrary
That's what I
element.
call vectors here. This is important to see that. I call a vector. Okay, what is a vector here? A prime is this matrix, 2 by 2 matrices. So A prime is, okay, so A prime is just the sum of the A's, A1 plus A2, B prime. Okay, so I'm restricting, yeah, that's right. I'm restricting my A's to be in the Grassmann algebra. You're right, I've confused that here. So the A's are linear combinations of the Grassmann element A1 and A2, or up to AN. And the B's, okay, but then, Okay, so, oh, no, I've changed that. No, okay, it's a little confusing. I made some mistakes, it looks like, because here I'm actually saying that the A's are vectors. Yeah. Okay, let's go down. You can see what happens here when I jump. These expressions I'm getting here. All right, let's see. So I'm really trying to calculate what happens for these. So normally in SL2, you look at the generators of SL2, you look at the matrix 1, -1, the matrix 0, 1, that's a generator. And the other generator is 0, 1 here. So in the Clifford algebra, you consider that to be B as a null vector, and A here, that's the normal product. That's where you assume that the A squared and B squared is 0. So notice that notice what happens in this expression. So if I take F comma G, that's FGF for these matrices, just the usual matrices. And the new product,
Yes, thank you.
well, A dot B is 1 in this case. So that's 1 plus 1. That gives me 2. But then these are zeros. Dot B 1/2. So I get 4 times a half is just, well, 1/2 squared is 1. And this is 0 because A squared is equal to 0 here. Now, anyway, you have to look at this. I've made several mistakes here, so I don't want to belabor too much. So really, I'm thinking about A and B here as being in the geometric algebra AN, BN. Yeah, GNN, the geometric algebra GNN. Well, in this case, G22. And it's only in the case when A squared and B squared are zeros that it reduces to the ordinary Lie bracket of these generators for SL2. So anyway.
There seemed to be an equation, maybe on the previous page, where you necessarily assumed that A squared was 0, but maybe I just misunderstood that.
Okay, well, that's why I'm not being so clear here. That's right. Here, when I wrote F, okay, that's an interesting case. So in this case, 7, I'm thinking about the A prime as being elements in the Grossman algebra. So then, of course, that would have square 0 because, A prime is now a real matrix. Oh, wait a minute. No, that's not true. No, that's not true what I just said, because A prime now is actually a linear combination. Well, F11 times F12, that would be a linear combination of A and B. So, okay, no, okay, I am assuming that it's in G11. It's the vector in G11. Okay. So that would be the case where I cannot assume that A squared and B squared are equal to 0 there. That's a separate assumption. But that's interesting to look at those special cases. So I get this final formula here when I let F be the matrix. Notice that this is the matrix of E3 as a polymatrix that represents the vector E3, right? 1 minus 1.
But could you just scroll up a little bit? Let's see here. Okay, there. Just no. Oh, no, not too much. Here. No, don't move. So it says, of course, the compatible null vectors. And then you write BA 1, 0, 0, 1.
That's what, yeah, when I say compatible or dual null vectors, that's when the A squared and B squared are equal to 0. So then, and the BA becomes an idempotent. So BA is equal to BA, BA squared is equal to BA, and BA cubed is also equal to BA. So I essentially get BA times the identity matrix 1, 1 then. So that's correct. So that's in the case where
But
you have
that's a special case.
or dual null vectors, what I call dual null. That's equation number 1. Okay, so we have dual null vectors. So this thing then reduces to BA times, so I can just factor it out then. This expression just reduces to the ordinary spectral basis then, because that's 0, okay? So that was our, okay, so this is correct, this is correct.
But the A is not necessarily a null vector.
No, in this case it is, because I say they're compatible null vectors. I should say satisfying equation 1, okay? That's
But
where I had
everywhere else in here, where you write A, say in the next line, you no longer are assuming that they're null vectors.
That's right. I'm no longer, I'm assuming this expression. So A prime is a linear combination of A and B. B prime is also a linear combination of A and B, which is saying really that F is in G11, okay? Because remember the vectors of G11, the Clifford algebra G11 are a linear combination of E and F, but E and F are linear combinations of A and B. Okay, so now I'm using the module when I write down this general expression here. I'm considering the same type of an expression as I get, but now A and B are vectors in G11. So they're linear combinations of the null vectors A and B, or AI and BI, or AI and BJ. So that's very important to understand that. And I haven't been that clear, I suppose. That's why I cannot reduce this. It's only when A squared and B squared are equal to 0 can I reduce that down to the usual case of just ordinary matrix multiplication. So I hope that this is revealing the structure of matrix multiplication. In fact, you could say that had Grossman or Clifford been recognized before Cayley introduced the matrix product, that Cayley would have seen the relationship between matrices and Clifford numbers. Had he studied Clifford material before he invented matrices, he might have done this, and this would not have indoctrinated us so thoroughly that we suffered up till this day by indoctrination of the last 200 years of, or 150 years of mathematics.
Okay. Well, I think that last section especially needs, at least from my point of view, I need more time to absorb that, I think.
Yeah, well, I should make it clear, but I do. Yeah, this is a little unclear here, but yeah, this is what I worked on the last week. Oh, I tried to change some of the earlier sections to reflect it too, but I think this is important, really. And I will probably mention it in this upcoming, my paper retains TAIN, that's correct. My upcoming paper really consists of that my talk will give to this CGA, AGA, CGA, or whatever it's called, consists of these 10 definitions here. So I use this material in my upcoming talk for the CGA, whatever it is called. That's in October.
Yeah.
But I won't mention this, but it's not in that.
I think we've gone on past our usual time as usual.
Okay.
So, but I think that you basically reached the conclusion. Or maybe you have a separate conclusion. I'm not sure.
No, well, like I say, my main conclusion is, I think my observation that had Cayley studied Clifford and developed Clifford algebra a little bit more, he would have done what I'm doing right now. He would have said matrices are the coordinate matrices of geometric numbers. Well, remember the term geometric algebra was used by Clifford himself. So it should be known as geometric algebra, and it can consider it to be the natural extension of the real number systems to include the most basic Clifford algebra are called the mother Clifford algebras of signature n, comma n, and they're algebra isomorphic to the matrices of dimension 2 to the n, 2 to the n over the real or complex numbers. Okay, so.
Okay. And it's very interesting and provocative. But it's also does, I mean, it's some serious detailed algebra to although all of the operations that you're describing are relatively elementary and defined axiomatically, to be sure that one applies all of those axioms at the appropriate time seems a bit challenging, maybe to me.
Well, that's the thing. As I say, I think that what stopped Clifford algebra is these terrible identities that you have to at least somehow master, some of them at least. But of course, now computer algebra is taking over. Now, I'm not versed in all these Clifford algebra programs that are out there now. All I use is Mathematica, but the identities are now much more manageable with computer help.
Mm-hmm. Okay, well, thank you very much for a very interesting presentation. We perhaps should discuss what presentation we might have in 2 weeks. Jesus, did you have anything in mind that you would continue in 2 weeks' time?
Yes, in fact, the provocative presentation of Professor Garret is good. No, I like to present something more about duality and interaction. Then I think that this subject is going in a parallel way of the presentation of Professor Garret. Then I like to prepare something and discuss with you.
Okay.
Okay,
That's
I'd
great.
be very happy with that. I think it'd be very interesting.
Okay, thank you.
Okay, so let's agree we'll meet again in 2 weeks and continue from there.
And I want to thank you both for being patient with me presenting it. It helps me in getting prepared for this next thing at CGA, whatever it's called. I appreciate that.
So see you both in 2 weeks' time, and I'll update that schedule to make sure it's accurate.
Okay, thank you very much.
Thank you.
Bye for now.
Bye.